Thank you, Minia. Thank you, Benjamin, and thank you to the SEA for giving us the opportunity to organize this session for the SINERGIAS SEA. In this occasion, we're going to talk about artificial intelligence applied to astronomy. As you all know, the progress of artificial intelligence in our research fields is undoubted, and astronomy is not an exception. Artificial intelligence and machine learning techniques have been applied to different fields of astronomy, from the sun to the cosmology. And the advantage relies on the precision and easy implementation, but also on its great efficiency to analyze very large samples of data, which are becoming more and more common in astronomy nowadays. In this session, we count with experts from across different fields of astronomy, and we aim to express and to make a summary of the impact that artificial intelligence is having on astronomy. We would like our speakers to tell us about their experience by using these analysis techniques on their research, but also on the challenges that they have faced. And we would like this event to be an opportunity to implement collaborations between different centers, to foster synergies between research groups, and to maybe coordinate networks which will help us to implement these techniques throughout our community. There will be 3 scientific talks with a turn of questions after each of the talks. You're welcome to ask your questions on the Zoom chat, and I will read them out loud. And then there will be an open debate with the speakers and also Carles Sierra, and we will try to focus on a more administrative or aspects, not so scientific, trying to talk about what are the opportunities for funding, how to collaborate with the private sector, but also we will address problems such as teaching, how to include all this knowledge in the curriculum for physics or astronomy, and how to improve the use of computing resources. As I said, this is aimed to be an open debate, so please post your questions after the scientific talks. And afterwards, during the debate, you're also welcome to post your questions and even to participate and say your experience and opinion on the open debate with the panelists. So it's my pleasure to have here an excellent group of scientists from different research topics. We have tried to cover all the range of astronomy fields, but this has been very difficult also because of time limits. So our excuses if there's some topic that we didn't cover. And if you have any interesting paper or result that you would like to share with us, please post it in the Zoom chat. So we will start this session with a talk. We're going from the local to the farther universe. So we're going to start with the sun and stellar physics with a talk by Andrés Asensio Ramos. Andrés is a researcher at the Instituto de Astrofísica de Canarias, IACEC. He also worked as a postdoc in Florence, and now he's back in Tenerife, where he has a staff position. And his interests are solar physics, but also Bayesian inference and stellar physics. And he's got a great publication record. So Andrés, the floor is yours whenever you want.
Let me unmute myself and share the screen. Okay. Okay, do you see the slides?
Yes.
Yes.
Okay, so thank you very much for having me on this interesting discussion. And let me start by saying a few words about the use of machine learning on the local part of the universe, on the solar and stellar physics. I'm a solar physicist, and I will try to do my best to show some examples of stellar physics or machine learning applied to stellar physics. So at least in solar physics, and I will give more examples in solar physics. In solar physics, the data is increasing exponentially. I think this is the same for the rest of fields. So we are facing the big data era, for instance, in solar physics from the 80s, where we had only one single pixel observation with a few wavelengths and a few observed times. Nowadays, we are reaching the megapixel images with many wavelengths covered and many times. And since everything is increasing exponentially, we expect to have much more problems in the near future. So if one makes a simple calculation of what is the time we need to analyze every single pixel in the observations for a typical observations, and since our models are usually complex, we will take of the order of 8 days to invert or to extract information from every single pixel in a normal observing day, which is, I mean, we cannot afford that, even if we go to 1 millisecond per inference, which is very far away from what we can do at the moment. So even if we scale that to many CPUs, given that we have access to supercomputers at the moment, we are really far away from reaching the necessary inference times for analyzing all the data we observe. So there is only a way out of that, and this has to be involving machine learning on the loop. Because, for instance, if we make a simple calculation, we need of the order of 100 microseconds per pixel. And if we want to obtain information about this pixel, and this is really far away, orders of magnitude far away from what we currently can do, even in supercomputers. So let me show a few examples. I prefer to show examples rather than just showing theoretical things. So let me go along these lines. First of all, how to do real-time data management, meaning that we have at the telescope systems that do the image correction or even extract information from the observations. From going to classification of events, which is important in solar physics if we want to detect events on the sun and then map them to geoactivity on the surroundings of the Earth, and then extraction of hidden information, extracting information that is not simple to extract using normal algorithms. Or to fast Bayesian inference, so to extract as much information as we can from the observations. So let me start with some examples of image correction. So when you go to the telescope, the world is noisy. So when you observe, especially polarimetry, and in our case in solar physics, you see images like these ones, in which you have the signal overlap with noise, which is never Gaussian and with no correlation. So if we want to clean this data, there have been efforts using machine learning to propose convolutional neural networks that can deal with this data cleaning. And here you can see how the neural networks extract the signals from the noise. And here you can see the difference, which is essentially noise. And you can see that the noise has a spatial correlation because these are essentially systematics. So this is important to have that in telescope so that the data you take home is clean. Or in our case, we need to get rid of the atmosphere. So we need online image correction methods like these ones, in which we also apply machine learning to accelerate this process. And then you can do things like this. So you have on the left hand side, you have the raw image you get to the telescope. This is an active region in the sun. And on the right hand side, you see what you get after correction. And then you increase a lot the spatial resolution and the contrast, which is important in many cases to detect events in the chromosphere of the sun or other stars. You can, I mean, we have applied this also to synoptic observations of the sun. And here you can see an example of how machine learning can be used to increase the spatial resolution of observations. the SDO satellite, which is observing the sun 24/7. And this is important because this gives the context information when you, of the events that you want to analyze on the sun. So this is done on the fly. So this is the neural networks that we train for that can be applied on real time. So this is essentially just an output of the satellite. You can just couple that with the observations. When you want to extract information from the observation, not only correct for the atmosphere or the noise, then machine learning is also being applied to this. And the advantage of deep learning is that you can produce the inference of physical properties from the observations almost on real time. If you see here that we are at the limit now of 700 nanosecond per pixel, the equivalent of that, which is very much, so it's much better than the limit, that the threshold we needed. So we are at the moment, we are with machine learning, with modern machine learning, we have reached that limit, so that we can analyze all the data on real time, meaning that we can analyze all the data you take in a single day, exactly that same day. And this has been a possibility only recently. And there are many options of how to deal with this problem, and there have been other efforts using normal perceptrons to do the inference, to extract information. And you can see here that they read, some people reach 62 microsecond per pixel, which is already below the limit that we need for extracting information on real time. And these perceptrons can be improved by using 2D information. But the important part is that we reach speedups of a factor of 10 to the 5 as compared with the classical inference method. So we are almost real time. And again, in solar physics, simpler methods of machine learning pre-deep learning era, like k-means, have been also applied to extract information from the transition region and close to the corona of the sun. And here is an example of how to extract things like the electron number density, velocities, temperatures from the observations of lines in the transition region observed with the IRIS satellite, which is also observing the sun since a few years back. As I said at the beginning, it's for the sun. We are living on the heliosphere, so it's important to classify which type of events happen in the sun, because they are essentially related with the geoactivity on the Earth. So if we want to predict what's going on the Earth, on the vicinity of the Earth, we need to classify the events that happen on the sun. And there have been some efforts using classification, deep learning for classification, trying to understand from images to classify of prominences, filaments, and active regions. And this is important because then later from this classification, you can go to a large telescope and point to that region and try to infer the magnetic field on that region, which is important to predict what's going on the Earth in a few days. Also, classification has been applied in stellar physics. I will do some transitions from solar physics to stellar physics, but you will see that many of the examples are in solar physics. And there have been examples of how to apply modern machine learning to classify what happens, for instance, from light curves, in which the light curves are unevenly sampled, which is typically the case when you go to a telescope. You don't have observations in a systematic way. You have observations whenever you can go to the telescope. So there have been some proposal of using recurrent neural networks to produce classifications of light curves, and they are working nicely. There have been some efforts of how to do classification of different type of stars from red giant branch or helium burning, starting from the power spectrum, which is giving information of how the star oscillates. And this allows us to produce a mapping that goes directly from this observed part of spectrum to the classification, and this is important to understand some properties of these stars, starting from asteroseismology. So let me show a few examples of how to extract hidden information from the observations. And one example is this one. We have the granulation, which is also going on in many other many types of stars, in this case on the sun. And the idea is how to extract velocity fields from the images. This is hidden from the view because I mean, you cannot measure velocities on the perpendicular plane, but you can train neural networks to do that, and we have done that, and we have detected small scale vortices in this in the sun, smaller than what you can do with normal techniques like correlation techniques. And you can also do things that look like magic in some sense, that is measuring what's going on the far side of the sun by measuring on the near side what the waves are doing on the surface. And you can apply machine learning to understand how are the active regions, or where are the active regions on the far side of the sun, which is important for extrapolating magnetic fields and understanding what will happen on the heliosphere, the geoactivity at a given moment. You can also try to extract hidden information from stellar spectra by just training autoencoders on millions of spectra, and trying to an autoencoder tries to reconstruct a spectrum from the original one by just going through a bottleneck, and then trying to understand if the bottleneck is giving you some information or extracting some information from the spectra. And indeed, you can see that some of the regions or some of the latent elements of this bottleneck are strongly related with physical quantities like the effective temperature, the gravity, or the radial velocity. And this is learned directly from data. You are not, this is not supervised. Bayesian inference has been accelerated a lot thanks to deep learning, thanks to the combination of machine learning and Bayesian inference. And there are a few examples of how to do that. And one of the examples in solar physics is how to apply invertible neural networks that can do the forward and the backward problem at the same time. And then you can, for instance, infer electron densities, velocities, or temperatures from the observations of events or in flares, from the observations of spectral lines of, in this case, H alpha or calcium-2 8542, and trying to infer not only trying to infer the probability distribution for all these quantities, and trying to inform whether they are correlated or not. And this is important because we lose information in the forward problem. These invertible neural networks have been also applied to stellar physics, and the idea is exactly the same, to apply these forward and backward neural networks and then extract information about, for instance, in this case, the age or the masses of stars from the observations of some measurable quantities. And then some other applications of deep learning are to, in this case again on the Bayesian framework, is to use them to accelerate the forward problem, which in many cases can take seconds, minutes, or even days to do. And then if you can bypass that using emulators trained with the deep learning, then you can accelerate the Bayesian inference. So let me finish, I think, on time by saying that not only solar, but also stellar physics are entering the big data era. And then we obviously need machine learning to do things like the fast synthesis, inversions, and classification, to do things like Bayesian inference or fast Bayesian inference that cannot be done in the normal case, or to do advanced detection of things that are apparently hidden from our view. But there are also some caveats that we can discuss later if we want, In many cases, there is a gap between the simulations and the real data, the simulations that we use for training and the real data that we later observe. And in many cases, we also have lack of data for training. And this impacts the quality of our machine learning algorithms. And thank you very much for your attention, and I'm open to questions.
Thank you very much, Andres, also for keeping on time. Very interesting results. Is there any question? Somebody would like to ask something? Please post your question in the chat. Sordorica says, one of the main problems in machine learning is data curating. How do you face this problem?
Well, in many cases, depending on if we need supervised learning, then we often use simulations for that. Simulations in the sun are in a descent state of in a descent state, so they are sufficiently close to the reality that we can more or less believe that they are a good representation of the sun. This is not always the case, and if you have simulations, then you can use them for training supervised methods. In other cases, we rely to unsupervised cases or self-supervised cases in which the loss function that we use for training imply the physics we expect in the process, and then you can then train your machine learning using essentially data and the physics, and that's probably the case in solar physics. But in many cases we are lacking good synthetic data for training. That's right.
Martin, I don't know your surname here. Martin says, when denosing new images from telescope, isn't there a risk of removing new events that were not present in the data set used for training or testing the machine learning method?
Yes, that's always there is always a possibility for that. You have to be very careful to have a look from time to time to the residuals and see if the residuals have some unexpected spatial resolution, and then focus on that. You cannot do a blind cleaning. You can do a blind cleaning for the normal observations, but if you are searching for, let's say, the zoology of events, then you have to focus on the residuals and check that the residuals look like the systematics you expect in your instruments. This has been the case. In fact, these people, when they apply these cleaning methods to solar observations, the residuals, they were surprised by the residuals because they look like what they expect the systematics were on the cameras. So they were rediscovering the systematics with by just machine learning. So that was interesting, but you always have to check that this is correct.
Thank you, Andres. Mark, you raised your hand.
Yes, I just wanted to ask a question. You described in many cases applications in which deep learning is used to accelerate or to make practical things that are impractical because of data volume, but that we know how to do them. It's just that they are too slow. Can you think of any application of deep learning which couldn't have been done without, and any discovery, for example, or any new thing in the field of solar physics that has been triggered by deep learning, more than accelerating stuff?
I think we are at the moment, so our inference codes are so complex because you have to include very complex physics on the process, that at the moment with machine learning we are only expecting to accelerate that process. We expect in the near future, if it makes some traction. Solar physics is a strange field in my point of view, and And the point is that they are not very keen on machine learning because they have been using complex codes for inferring physical properties for a long time. So, but I think, for instance, the example I showed on how to estimate velocity fields from continuum images of the sun, this is something that is not possible at the moment. I mean, it's not possible to do with the standard methods because if you apply local correlation tracking for that, you need to smooth out for a long time and for also large spatial volumes in order to get rid of the noise. And the deep learning approach produces per pixel and per time step predictions of the velocity field. This is something that is very far away from what you can do with normal methods. So this is probably the first use of deep learning in which we did something that couldn't be done with normal techniques. But I expect in the near future to have many more examples. So if we meet again in 5 years' time, then I expect to have this list, a long list, and need half an hour or an hour to tell you about that. So